Welcome to today class of nonlinear vibration. Today we are going to discuss on this bifurcation of periodic responses, also introduction to quasi-periodic and chaotic responses with the help of some examples. So, last class we have studied about different type of equations, Duffing equation, Van der Pol equation, Hales equation and Matthew equation, and we know in these equations in addition to fixed point response we are going to get periodic and quasi periodic or chaotic responses. So, in case of the periodic response, so the response so if you start at a time t and it has a period of capital T, then the response is said to be periodic then if x t plus t equal to x t. That means, if it repeats then it is known as a periodic response. So, in this case it has a minimum period of t. So, it can form a closed orbit and could be treated as a fixed point in Poincare section. So, if you take the Poincare section of a periodic response, then we will get a single point. So, this is a periodic response. Its phase portrait is shown to be a closed loop. In case of a 2 periodic response, so we have 2 loops. So, in case of a single periodic, a single loop is there, and in case of a 2 periodic, so we have 2 loops. Similarly, for higher periodic, so we will have number of loops. So, we have already discussed about the limit cycles. So, a periodic solution is said to be limit cycle if there is no other periodic solution sufficiently close to it. So, those things already we have discussed, and we have seen how in case of this Van der Pol equation we are getting a periodic or limit cycle. So, this is a limit cycle obtained in case of the Van der Pol equation, and also we have discussed that how to obtain the subcritical and supercritical subcritical and supercritical Hopf bifurcation points, and we know in case of the Hopf bifurcation. So, a fixed point response become unstable and a periodic response emanates from that point. So, here the fixed point response becomes unstable and we have a periodic response. So, if the resulting periodic response, if it is stable, then we have a supercritical Hopf bifurcation, and it becomes unstable. So, we have a subcritical Hopf bifurcation. So, those things already we have discussed in our previous lectures, and so today class basically we will study about quasi periodic responses particularly, and before that let us revise what we have studied about the stability of periodic system. So, to determine the stability of the periodic system, so if we are taking a system x dot equal to f x m, so where m is the control parameter and x is a function. So, x is a periodic solution, then we can perturb it, and after perturbing that thing, so we can get this matrix A matrix, and after getting this A matrix which is periodic, so we can obtain the monodromy matrix. So, this monodromy matrix can be obtained by taking some initial condition. So, by taking a initial condition phi initial condition, and we can obtain. So, we have to find this monodromy matrix phi equal to y t, taking initial condition this y 0 equal to I, that is unit vector. So, we can find this phi. So, that is the monodromy matrix, and eigenvalue of the monodromy matrix will give us information regarding whether the system is stable or unstable. So, if the eigenvalues of the monodromy matrix phi are called the Foucault multiplier, and there is a unique set of Foucault multiplier associated with matrix A. So, each Foucault multiplier provide a measure of local orbital divergence or convergence along a particular direction over one period of closed orbit. So, this thing we have discussed last class. So, how to obtain this thing also we have seen, and we have also seen this example how to find this Foucault multiplier. So, by getting this Foucault multiplier we can study the stability and bifurcation of this thing. So, we know that a hyperbolic periodic solution, we can tell a solution to be hyperbolic periodic when only one Foucault multiplier is located on the unit circle. So, if we plot the unit circle, then this is real and imaginary part. So, this is real and imaginary. So, if one root lies on the unit circle, then it is hyperbolic periodic solution. If two or more Foucault multiplier are located, then we are telling this to be non-hyperbolic. And in case of this, to study the bifurcation of the periodic response, so first we have to find the monodromy matrix, then we have to find the Foucault multiplier, then we will check whether the solution to be hyperbolic or non-hyperbolic. Then in the control space, we have to check whether the bifurcation what we are obtaining is the types of bifurcation we can discuss. So, in case of the bifurcation, there will be a qualitative or quantitative change in the stress control space. So, a bifurcation is said to be of co-dimension m. So, if it requires m independent control parameter to occur, then we tell this bifurcation as co-dimension m. So, a bifurcation that require at least m independent control parameters to occur is called a co-dimension m bifurcation. So, last class also we have discussed about transcritical symmetry breaking or cyclic fold bifurcation will occur if the Foucault multiplier, one of the Foucault multiplier leave this unit circle through +1. So, this is transcritical symmetry breaking or cyclic fold bifurcation, and in case of the period doubling bifurcation, so one of the Foucault multiplier leave this unit circle through -1, and if a pair of complex conjugate leaves this unit circle, then the resulting bifurcation will be secondary or off or Neymark bifurcations. And so, last class we have discussed about all these bifurcations, and today class we will start with what we mean by quasi-periodic response. A brief introduction to quasi-periodic response and chaotic response will be given, and then we will discuss one example to show how this fixed point response, periodic response and chaotic response occur in the system, and how the system behaves when these type of responses occur, and what we mean by the stability of this fixed point, periodic and quasi-periodic response. So, in case of a quasi-periodic response, the solution, let the solution x t. So, if we can write this x t equal to x 1 sin omega 1 t plus x 2 sin omega 2 t, if these frequencies omega 1 and omega 2. So, if these frequencies are incommensurable, that means the ratio between these omega 2 by omega 1 is an irrational number. So, for example, if you take omega 1 equal to 2 and omega 2 equal to root 2, then this ratio, that is omega 1 omega 2 by omega 1, which is equal to root 2. So, then we can tell that these frequencies are incommensurable. So, if these frequencies ratio, for example, in the previous example we have taken omega 1 equal to 2 and omega 2 equal to 4, then this ratio 4 by 2 equal to 2 is an integer. So, or we can so they are commensurable. If this ratio are commensurable, then we can get periodic response, but if this ratio are incommensurable, that is if the ratio is irrational number. So, in that case the response what we will get will no longer be periodic. So, they will be aperiodic, and these responses. So, one such response is shown here. So, by plotting omega 1 equal to 2, omega 2 equal to 2 root 2 and x 1 equal to x 2 equal to 5. So, this shows the response. So, in this case one can observe that the response is not periodic. So, if we plot the phase portrait, so one can see the phase portrait will look like this. So, it will look like a torus. So, as if there is a wound between these two, and it will fill up this space. So, it will be in between these two in between these two curves we can get this period or this phase portrait. So, this is if we plot y versus y dot, the response, the y versus y dot, the phase portrait will look like this. So, if we take Poincare section of this thing, so how to take Poincare section? So, we have to take this Poincare section, we have to find the minimum time. So, minimum time period. So, in this case omega 2 equal to 2 root 2. So, we have this T 1 equal to 2 pi by omega 1. So, this is equal to 2 pi by 2. So, this is equal to pi, and T 2 equal to 2 pi by 2 root 2. So, then it becomes pi by root 2. So, in this case our T 2 is the minimum time period. So, by taking T 2, or if we sample this response curve, if we sample this response curve with this T 2 time period, then the resulting response, if we plot the phase portrait of the sampled time response, that means we will sample it at an interval. Let us start with this point. Starting with this point, if we sample it with pi by root 2, then one can observe that the resulting curve will be a closed loop. So, the resulting curve will be a closed loop. So, in case of the quasi periodic response, so one can obtain a closed loop in case of drawing the Poincare section. But in case of periodic response, for example, if we have periodic response y equal to sin 2 t, then or sin 2 t plus sin 4 t. So, by taking this T 1 equal to, so T 1 equal to 2 pi by 2, that is pi, and T 2 equal to 2 pi by 4, that is pi by 2. So, if we sample it with pi by 2, so we can see, so from these two curve, if one plot, then one can obtain the response, or one can obtain the Poincare section to be. So, the Poincare section, if one plot in case of let y equal to sin 2 t plus sin 4 t. So, in this case the Poincare section, if I want to plot this y dot versus y. So, this plot, if I plot for sin 2 t and sin 4 t, if we sample it at pi by 2. So, let us find. So, we are sampling it at, so we will start at 0, then pi by 2, then pi, then so pi plus pi by 2. So, this is 3 pi by 2, then 4 pi by 2, that is 2 pi, and if you go on increasing this thing and find the function y. So, at 0, so this is 0. So, at pi by 2, so at pi by 2, so this becomes pi. So, sin pi equal to 0, and this sin, so this becomes sin 2 pi. So, this also becomes 0. So, in this case if you take, we can find 2 points. So, we can find 2 points on this curve. Okay. So, but in case of this quasi periodic response, so instead of getting 2 points, so we will get a closed loop. So, in case of periodic response, so depending on the frequency or number of frequency present in the response, we can get definite number of points on the Poincare section, but in case of the quasi periodic response, a 2 period quasi periodic response is known as torus. So, this is a torus, or one can write this as 2 t. So, in torus, the Poincare resulting Poincare section is a closed curve. So, this is so one can get, so for example, let us take this equation, the second order equation. So, this can be thought of as a spring mass system with a nonlinear spring. Along with that, so the external forcing are cos 2 t plus cos 2 root 2 t. So, if one plot this, so to use this or to use the numerical methods, we can we can write the second order differential equation using a set of first order differential equation. The first order differential equation, first equation one can write x 1 dot equal to x 2 and second equation, that is x 2 x double dot. So, that will be equal to minus x minus 2 x dot minus x cube minus cos 2 t minus cos 2 root 2 t. So, one can write, so x 2 dot will be equal to minus of x plus 2 x dot plus x cube plus this cos 2 t plus cos 2 root 2. So, if one plot these curves, one can find. So, this shows the x versus time and this is the x dot versus time. So, x versus time and x dot versus time are shown in this figure, that is x 1 and x 2. So, if one plot x 1 and x 2, this is the curve, and also, so this is a program, MATLAB program written for plotting this time response, and also one can find the Poincare section in this case. So, this is the phase portrait. So, this is the phase portrait, that is y dot versus y, and this is for another case, that is x t equal to 5 sin omega 1 t plus sin omega 2 t. So, omega 1 equal to 2 and omega 2 equal to 2 root 2. So, in this case, this is the Poincare section. So, here it is section with time period pi by, so 2 pi by 2 root 2. So, this becomes pi by root 2. So, by sampling it at pi by root 2, so one can see or one can observe of getting a closed curve. So, in this way one can obtain the Poincare section or one can plot the phase portrait. So, unlike in case of periodic response, where the Poincare section give definite numbers of points. So, here one can obtain a closed loop. The closed loop may not be circular. So, depending on the presence of harmonics, the loops size will be different or shapes will be different. Okay. So, these are some of the example. So, here, so in this example, omega 1 equal to 2 and omega 2 equal to 2 root 2, and we are plotting x t equal to sin 5 sin omega 1 t plus sin omega 2 t. So, this is the response and this is the Poincare section. Similarly, if you take omega 1 equal to root 2 and omega 2 equal to 2 root 5. So, this is the ratio is root 5. So, previously ratio was root 2. So, this is the response. So, this is the corresponding Poincare section and time response. So, there is so the time response is shown here 0 to 10, and in this case the time response also 0 to 10, but the as the frequencies are different. So, the curves look slightly different. Okay. So, also another plot is plotted. So, by taking this omega 2 equal to 2 root 11, here the ratio is root 11. So, here the ratio is root 5 and here it is root 2. So, depending on this, so one can get different type of this torus. So, already we know the Poincare section in case of this quasi periodic response, and in that case we have discussed that one will obtain a closed loop. So, associated with this quasi periodic response, so there is a number that is known as rotational number. So, when we plot this Poincare section, let us start with the Poincare section, this is P 1. So, let us start at a point. So, we have start at a point. So, this is the x point. So, we have started at a point this. Now, in the first iteration, let the point, this is the point. In the second iteration, the point is this, third iteration, the point is this. So, we go on sampling this thing, and so with each iteration we got one point, and so one can obtain several points on this loop. One can get several points on this loop if one find the Poincare section. So, taking x as the initial point. So, let p I x a discrete point obtained after ith iteration of the Poincare map. So, one can define this rotational number as the, so this is a discrete point on a Poincare section of a 2 periodic quasi periodic So, to obtain this rotational number, so first we have to plot this curve and check where which iterations, after what iteration. So, the same point arrives. That means, in this case, so if we have started at this point and we have seen in the first, when we have come across this loop. So, we have seen P 7 after P 7 and P 8. So, let us have this P. So, this is P 6, P 7 and P 8 will be somewhere here. So, P 8. So, let this is the starting point. We have P 1, P 2, P 3, P 4 and let we have P 5, P 6, P 7 and then we have this P 8. So, if this point lies between the 7 and 8, we can tell this rotational number to be 7. So, let I k minus 1th and I kth iterate, let k I minus 1 and let I k minus 1 and I k iterates bracket this x. After we go k times the closed loop, then this winding time T w can be written as limit k tends to infinity I k k. So, if k is 1, so let us take k equal to 1, that is in the first k. So, once we have come across this loop. So, once we have come across the loop, so this point or this point x is bracketed between P 7 and P 8. That is why we can tell the rotational or winding time and rotational number in this case this way. So, this T w will be equal to I k by k. So, I k, let I k minus 1 and I k iterates bracket the x after we go k times. So, in this case k equal to 1. So, if once we have moved this, then this I k, this k minus 1, this becomes 7 and I k becomes 8. Okay. So, we can tell this is limit k tends to infinity. So, this will be then 8 by 1. So, this will be 8. So, similarly, we can let in second iteration. So, we can find which two iterates bracket this point, similarly in third. So, if we go k times, then if we average that thing, that means limit k tends to infinity I k by k. So, we will get this winding time. So, the reciprocal of this winding time is known as the rotational number. So, rotational number is the reciprocal of the winding time, that is 1 by t omega. So, 1 by t omega. So, this is equal to 1 by 2 pi, limit k tends to infinity I equal to 1 to k. So, alpha I by k also. So, one can find this thing also by taking a internal point and checking what is this angle. So, angle which bracket this and this point. So, by finding this angle also one can tell about the rotational number. So, this will be equal to 1 by 2 pi limit k tends to infinity alpha I by k. So, alpha I, that angle what we have shown. So, that is alpha I, and one can find using this a point in the interior of this loop and find the rotational number. So, rotational number is reciprocal of winding number, and after finding the winding number one can find this rotational number. So, winding time represent the average number of iterates required to get back to x bar. So, we have taken starting point x and the winding time represents the average number of iterates required to get back to x. The inverse of the winding time is called winding number. So, in this way one can study or one can find the quasi periodic response, and after obtaining the quasi periodic response, as we have seen, the Poincare section of the quasi periodic response is a periodic response or is a closed loop. So, one can study the stability of the quasi periodic response by studying this closed loop also. And now, let us see, after studying this fixed point response, periodic response and quasi-periodic response, the other remaining type of response in case of a nonlinear system is the chaotic response. So, a chaotic solution is a bounded steady state behavior that is not an equilibrium solution or periodic solution or quasi-periodic solution. So, a chaotic attractors are complicated geometrical object that poses fractal dimensions. So, unlike spectra of periodic and quasi-periodic attractors, which consist of a number of sharp spikes, the spectrum of chaotic signal has a continuous broadband character. So, in addition to the broadband components, the spectrum of a chaotic signal often contain spikes that indicate the predominant frequencies of the signal. So, the major difference between this periodic, quasi-periodic or fixed point and this chaotic response is the sensitivity to initial conditions. In case of the chaotic response, it is very sensitive to the initial condition. In case of a fixed point or periodic response, so whatever may be the initial condition at steady state, it does not depends on the initial condition. But in case of the chaotic response, it is very sensitive to initial condition and one can observe a butterfly effect in case of this chaotic response. That means, by slight change in this initial condition will lead to another type of response which is not at all similar to the response obtained in the previous iterations. So, to know more about this chaotic response, one may refer the book by Nafe and Balchandran. So, one may refer this book by Nafe and Balchandran, that is Nonlinear Dynamics, the book Nonlinear Dynamics, and so these portions have been adapted from this book by Nafe and Balchandran, Nonlinear Dynamics. So, a chaotic motion is the superposition of a very large number of unstable periodic motion. Thus, a chaotic system may dwell for a brief time on a motion that is very nearly periodic and then may change to another periodic motion with period that is k times that of the periodic preceding motion. So, this constant evolution from one periodic motion to another period produces a large time impression of the randomness, while showing a short term glimpses of the order. So, that means, we know that these chaotic solutions are neither fixed point response, periodic response or chaotic quasi-periodic response. They depend very much on the initial condition, and there are several routes to this chaotic solution or chaotic response. So, few of them are. So, one is this period doubling route to chaos. Chaotic response also obtained from this quasi-periodic response. So, either a torus breakdown, either it may be a torus breakdown route to chaos, or it may be a torus doubling route to chaos. So, like period doubling to route to chaos, similarly also torus may double up or torus may add up to give rise to chaotic response. Also, it may break down to give rise to chaotic response. Also, intermittency and crisis are other routes to chaos. So, one can obtain chaos due to these routes. So, one can obtain, so by changing these control parameters, sometimes a period doubling leads to chaos. So, those things we will see with the help of some examples. For example, let us take, so this is a period 2 period response and now it becomes 4 period. So, then 4 will becomes 8 and 8 will become 16, 16 32. So, in that way the period will double to obtain a chaotic response. So, this is a periodic, so this is a response with several periodics, for example. So, it contains 16 periodic. So, 16 periodic. So, the orbits have been or closed loops have been marked. So, this is 1, 2, similarly 3. So, this way all the orbits are marked So, here there are 16 orbits. So, these 16 orbits, so you just see the phase portrait. So, that is y dot versus y, it looks like a chaotic response. So, if we go on doubling this period by changing the system parameter or control parameter, we can land up with a chaotic response. Similarly, you can see this is a Roger equation. So, in case of the Roger equation, so which is this slides has been taken from this Wikipedia. So, where the equation can be written this way: x dot equal to minus y plus z, y dot equal to x plus a y, and z dot equal to b plus x minus c into z, where a, b, c are constant. And if one plot this, so if one plot in x y plot say, so one can obtain initially for c equal to 4, one can obtain a period 1. So, by changing c to 6, the c parameter to 6, one can obtain a 2 period, and then by changing it to 8, one can obtain a period 4. So, c is 8.5. So, then c equal to, so by taking this c equal to 8.7, so this becomes period 8, and c equal to 9, one can see the response to be chaotic, and again c equal to 12. So, one can see this is a period 3 response. So, then c equal to 12.6, period becomes 6, c equal to 13, again it becomes chaotic, and c equal to 18, the chaotic response continues. So, this is the chaotic response which which looks like a funnel, or it is known as Roger funnel. So, one can obtain a chaotic response. And if one plot the Poincare section, so for a periodic response, we can obtain a single point. For 2 periodic, so we can obtain 2 points. That means c equal to, so if you go on increasing c equal to 4 to 6, so at c equal to 6 we obtain 2 points. So, initially we have a single point, so it continue. So, from a single point to, so you go on increasing, so the single point becomes 2 points. Now, these 2 points becomes 4 points, and 4 becomes 8, and 8 becomes 16 to make the response chaotic. And here you can see, so there are some windows. So, in this case 1, 2, 3, 4, 5, 6. So, it is connected at these 6 points, and in this case you can see, so these are the period 3 windows. So, only at 3 points it is connected. So, 3 points we are getting. So, in this range we are getting only 3 points, but here we are getting several points. So, here we have window. So, 1, 2, 3, 4, 5 windows here. Similarly, one can count this thing 1, 2, 3, 4, 5. So, number of windows can be counted at these points, and one can see between this chaotic response one can get some windows of periodic response. So, this is a period doubling route to chaos. So, here initially one has a periodic response. Now, by changing this parameter c in this Roger equation, so one can obtain 2 period, then 4 period, then 6 period, 4, then 8, then 16, and it continues. And if one plot the Poincare section, one can see clearly the behavior to be chaotic. So, unlike a quasi periodic response, where the Poincare section is a closed loop. So, in case of chaotic response, the Poincare section will fill up the space. So, one can distinguish the Poincare section of a periodic response, quasi periodic response, and chaotic response. So, in case of a periodic response, it will be single period or a definite number of points, and in case of quasi periodic response, it will be a closed loop, and in chaotic response, it will fill up the space. So, if you plot the phase portrait, so x versus x dot. So, let us plot this thing for these 3 different things. So, for a periodic response, single period 1 point, let 2 period, then you will have 2 points. For 3 period, there will be 3 points. That means, definite number of points will be there. So, in case of the periodic response, the Poincare section will contain definite and in case of quasi periodic response, so it will be a closed loop. So, it will be a closed loop. So, quasi periodic response, and in case of chaotic response, the response will fill up the space, the response will fill the whole space. So, this is y dot versus y dot versus y in case of, or x dot versus x phase portrait. So, this is a chaotic response. So, in case of period doubling, so a number associated with this period doubling root 2 chaos is Feigenbaum number. This Feigenbaum showed that the sequence of period doubling control parameters value scales according to the law delta equal to limit k tends to infinity. So, alpha k minus 1 by alpha k plus 1 minus alpha k equal to a universal constant which value is 4.6629216. So, this number is known as Feigenbaum number. That means, so one can observe let alpha k. So, the period, so kth period occur at a control parameter of alpha k, then and k minus 1th period was at k alpha k minus 1, and in this case, for example, in case of this Roger funnel. So, we have this period doubling at c equal to 6 and it becomes 4th at 8.5 and this becomes 8 and 8.7. So, if you take k equal to, so let us take this one. So, alpha k, that means this 4th period 4, it becomes 4 at 8.5 and this becomes, so this becomes 2, that means the previous iteration this 6 at k equal to 6, that means alpha k minus 1 is 6, alpha k equal to 8.5 and then alpha k plus 1 equal to 8.7. So, if one find this ratio, that means 8.5 by 8.5 minus 6 by 8.7 minus 8.5. So, that means 8.5 minus 6 by 8.7 minus 8.5. So, this becomes, so 2.5 by, so 0.2. So, 2.5 by 0.2. So, in this way one can find this number. So, one can check that this number is a universal constant, that is alpha k minus 1. So, by alpha k plus 1 by alpha k will be equal to 4.66292016. So, in this example, so as they are not the critical point, so this value is coming to be. So, these are some example, this is only some example shown. So, as these are not critical points, so this number multiplying 5 here, multiplying 5. So, this becomes 1 and this becomes 10 plus 2.4, 12.5. So, one can obtain the Feigenbaum number like this, but this example as we have taken this number arbitrarily. So, this not the Feigenbaum number. So, we are getting a ratio of 12.5. So, if one find the critical parameter, then one can obtain that number to be. So, critical parameters will be here. So, this is one critical parameter. So, this point. So, now it becomes, so initially this was 0, initially it was this was single period, now this is double period and this period will be 4. So, now this point it becomes 4. So, one has to take this value and now it becomes 1, 2, 3, 4. So, 2 to 4 and this 4, 8. So, at this frequency. So, what is this frequency one can find. So, at this frequency it becomes 8. So, this ratio. So, if this is k, then alpha k. So, this value if it is alpha k. So, this is alpha k minus 1 and this is alpha k plus 1. So, the ratio alpha k minus 1 by alpha k plus 1 minus alpha k. So, this ratio will be a constant or is a constant, and that is known as Feigenbaum number, or this number equal to 4.66292016. So, in this way one can predict when the next doubling will occur. So, if you know doubling occur at a particular point, then we can predict the next period doubling bifurcation or period doubling critical parameter. So, similarly, one can find the other different routes, that is torus doubling route to chaos, torus breakdown route to chaos, and also different crises. So, through one example now we will study this bifurcation of fixed point, periodic, quasi periodic and chaotic response, and we will conclude this module. So, this is one example taken from the work by Professor R.C. Kaur and S.K. Dwivedi, which was published in this International Journal of Nonlinear Mechanics in year 1999. So, this is a slender beam. So, a slender beam base, excited slender beam, which contain one arbitrary mass. By positioning this mass at different locations, so one can change the frequency of the system, and for some values of these frequencies, so one can, as this is a continuous system, so one can get infinite number of natural frequency of the system, and these natural frequency may be distinct, or sometimes they may have integer relations. That means, this omega 2 by omega 1 or omega ratio of omega 1 is to omega 2 is to omega 3 will have some integer relations. For example, omega 2 by omega 1 may be equal to 3:1, omega 1 is to omega 2 is to omega 3, it may be equal to, so it may be equal to 1:3:5, or omega 1 is to omega 2 is to omega 3 may be equal to 1:3:9. So, in this case, when this omega 1 is to omega 2 equal to 1:3, so one can obtain one internal resonance of 1:3 type. So, in case, or this will be a 2 mode interaction, and if the ratio, that is omega 1 is to omega 2 is to omega 3 equal to 1:3:5, 1:3:5 or 1:3:9. So, in these two cases one can obtain internal resonance of third mode. So, one can obtain internal resonance 3 mode interaction. So, one can have, so in this case 3 mode interaction, and in this case one can have 2 mode interaction. But when these frequencies are very distinct, so there will be no internal resonance, and one can obtain these response of the system by considering single mode approximation. So, either one can go for a single mode approximation or 2 mode approximation or 3 mode approximation, depending on the ratios of the frequencies obtained in this case. So, in this case, by positioning this attached mass at a different locations, so it has been observed that the system can have these 3 type of modal interaction. That means, without modal interaction, second 2 mode interaction, and in case of 3 mode interactions also it has been obtained 1:3:5 internal resonance and 1:3:9 internal resonance. So, the system, that is a base excited cantilever beam. So, it is excited periodically at this base, that is ZT. So, ZT equal to, so one can write this ZT equal to Z0 sin omega t. So, here with a amplitude Z0 and frequency omega, the base is excited. So, when the base is excited, the system move in a transverse direction for some value of this Z0 and omega. So, for some value of Z0 and omega, so it will vibrate in just, it will oscillate or it will move up and down, but if this value for some critical value of z0 and omega, when it exceeds this critical value, it vibrates in a transverse direction. So, in this work, the response of the system is obtained. So, the response of the system is obtained for this 3 modal interaction, and one can observe this fixed point response, periodic response and chaotic response also in this case. So, let us take this example. So, in this example, so the equation motion of this system can be written by this way, that is equal to u n double dot plus 2 epsilon zeta n u n dot plus omega n square u n minus epsilon m equal to 1 to infinity f n m u m cos phi tau plus epsilon k equal to 1 to infinity, L equal to 1 to infinity and m equal to 1 to infinity alpha k l m n u k u l u m plus beta n k l m u k u l u m. So, beta k n k l m u k u l dot u m dot, one can note that here these are the velocity term. So, in this case product of 3 displacement term and k l m are the modal displacement, kth mode displacement, lth mode displacement and mth mode displacement. Similarly, this is gamma n k l m u k u l u m double dot. So, in this case you just see, so this part is the geometric nonlinear term, as these two parts, this product of two velocity as it gives acceleration. So, this is also inertial nonlinearity and this is also inertial nonlinearity. So, one can observe this two inertial nonlinear term and a single geometric nonlinear term in this case. So, here this nonlinearity is coming due to the large transverse displacement of the system. So, this is the temporal equation obtained by applying Galerkin method to the system. So, here one can see the coefficient of, so one can see the coefficient of u m, that is the displacement is f n m cos phi tau, that is a periodic term. A periodic term is the coefficient of u m, that is the response. That is why this type of system are known as parametrically excited system. So, unlike fixed unlike in case of the force vibration. So, where the resonance occur at a frequency when it is equal to that of its natural frequency, in case of the parametrically excited system, the resonance may occur when it is away from the natural frequency also. So, one can obtain a response. So, for example, in this case by taking this phi equal to, so if I will take phi equal to omega m plus minus omega n, the resonance can occur at these cases. So, if taking this m equal to 1 and n equal to 1 or m equal to n, so one can obtain phi equal to, so 2 phi will be equal to 2 omega n. So, if n equal to m, so phi equal to 2 omega n, and this type of resonance conditions are known as principal parametric resonance condition, and if they are not same, so if it is plus, then it is known as combination parametric resonance, and when we are taking this negative sign, this is combination resonance of difference type. When we are taking it plus, then it is combination resonance of summation type, sum type. So, let us see the case of the principal parametric resonance. So, in case of principal parametric resonance, taking this phi equal to 2 omega 1 plus epsilon sigma 1, where sigma 1 is the detuning parameter, and as we are considering two mode interaction, that is omega 2 nearly equal to 3 times omega 1, then we can also take another detuning parameter epsilon sigma 2. So, sigma 2 is the detuning parameter, epsilon is the bookkeeping parameter. So, this omega 2 equal to 3 omega 1 plus epsilon sigma 2. So, by taking these things, so one can obtain a set of, so one can obtain a set of 4 equations. So, these are the 4 reduced equation one can obtain. So, this is the first one, second one, third one and fourth one. So, these are the 4 equation one can obtain using method of multiple scales, and in this equation one can see this is A dash, gamma 1 dash, A 2 dash. So, A 2 dash and So, this is A2, this is A1 dash, gamma 1 dash and A2 dash, and we have gamma 2 dash. So, for steady state we can put this A1 dash, A2 dash, gamma 1 dash, gamma 2 dash equal to 0, where A1, A2 are amplitude and gamma are phase, to obtain a set of algebraic or transcendental equations, and by solving these equations one can obtain the fixed point response. And by solving these equation directly numerically, one can obtain the periodic response. So, initially first one has to plot the fixed point response. In this case, as we have 4 equations, so numerically one has to solve these things, and one can see in this case if we perturb it, the perturbation will not contain. So, for these cases the perturbation will not contain, as we have this A2 gamma 2 dash term and A1 gamma 1 dash term, the perturbation will not contain these terms. So, to avoid this thing, one can make the transformation by taking P I equal to A I cos gamma I and Q I equal to A I sin gamma I, where I equal to 1 to 2, and one can write these 4 equations by using P and Q. So, instead of writing in terms of A and gamma, one can write these equation in terms of P and Q. So, one can have a set of equations, 4 equation in terms of P and Q. Now, by solving these equations, one can study its stability. By perturbing these equations, one can study its stability, and solving those algebraic equation or transcendental equation, one can get the response. So, this is a typical response shown. So, one can see several branches of the response there. So, unlike in case of the Duffing equation, one can get with cubic nonlinearity, one can get only 2 branches. Here several branches have been obtained and several bifurcation points are also shown. So, for example, this point and these points are half bifurcation point, and in this half bifurcation point one can obtain the periodic response. So, here one can see at this point, if by taking this parameter, control parameter phi, so if one find the response, one can see the periodic response. Similarly, this is a saddle node bifurcation point and these points are pitchfork bifurcation point. So, here you just one can obtain or one can observe that one has a supercritical pitchfork bifurcation up to this, and at this point one has a saddle node bifurcation, and at this point one can has a, so one can have, so this is stable and this becomes unstable. So, one has a subcritical pitchfork bifurcation, while this is supercritical pitchfork bifurcation, this is a subcritical pitchfork bifurcation. Similarly, so this point has been, so the previous point has been expanded. So, this is the point expanded, and to show clearly what is happening in this trivial state. So, this is the trivial state. So, trivial state becomes unstable here, and again it has a stable and unstable range. So, unlike in case of with a single mode interaction, one can see, so here a set of stable and unstable response, trivial response obtained in case of this 2 mode interaction. So, this is with gamma, gamma is the forcing function. So, these are with the frequency, this is forcing function, one can obtain this response, and here at this half bifurcation point one can see the period doubling root 2 chaos. So, this is single period, this is 2 period, and this is chaotic response. Similarly, so this is the Poincare section showing the sequence of period doubling root 2 chaos, and these responses are clearly chaotic here. So, one can observe this chaotic, this is a chaotic response. So, this chaotic response after changing this control parameter comes in contact with a unstable fixed point response, and one can observe here the maximum value is 30, here the maximum value comes to be 100. So, when it comes in contact with an unstable fixed point, then it explodes, and one can obtain a bigger attractor. So, this chaotic response now is inside in this bigger chaotic response, and this type of breaking of this chaotic response or this merging or this type of chaotic behavior is known as crisis. So, when this chaotic response come in contact with an unstable fixed point response or periodic response, it explodes and one can obtain this interior crisis. So, this previous chaotic attractor is in the interior part of this bigger chaotic attractor. So, this is interior crisis. Similarly, so before bifurcation, this is one chaotic attractor. So, by changing this, so let at 1.81 phi equal to 1.81. So, one can observe two sets of chaotic attractor. This is one set and this side also will be another set, and by changing this phi to 1.79, one can see that these two chaotic attractor merge to form a attractor merging crisis. Similarly, one can observe different type of cascade of. So, initially we have a torus, then this torus doubling root 2. So, one can obtain a torus doubling root 2 chaos in this case by changing this parameter. Also, for combination resonance, so this is a set of fixed point response. So, from this fixed point response one can plot this bifurcation diagram. So, after plotting this bifurcation diagram, one can see, so these are different limit cycles, and so this is a set of, so this is a set of periodic response. So, symmetry breaking, so one can see this symmetry breaking root 2 chaos. So, initially we have a symmetric periodic response, and by changing the system parameter we can have a chaotic response. So, this is another symmetry restoring crisis, and one can observe a butterfly effect by changing this initial condition, chaotic response one can obtain. So, this is one example where we have seen this initial torus breakdown root 2 chaos. Initially we have a torus, by changing the system parameter this torus breakdown, and finally, so this torus this is the Poincare section. In this Poincare section one can see a closed loop. These loops slowly it breaks and finally it becomes chaotic. So, this work was published in Journal of Sound and Vibration, and this is a torus breakdown root 2 chaos. So, it is shown in P1 Q1 portrait, phase portrait or state space. So, this is also another time response showing alternate. So, you can have alternate periodic and chaotic response, intermittency to show the intermittency. This is one example of attractor merging crisis. Similarly, in case of 3 mode interaction also one can observe different type of chaotic response. So, here the initial chaotic response come in contact with a unstable fixed point and it explodes to a bigger attractor. So, similar to Roger funnel, here also in this simple example of a cantilever beam, base excited cantilever beam. So, one can obtain this chaotic response which is similar to that of the funnel. So, here also one can obtain different. So, it travels or it switches between different unstable periods or different unstable orbits to give a chaotic response. So, with this example, so we know the types of responses, that is fixed point response, periodic response, quasi periodic response and chaotic response exhibited by a nonlinear system. So, and also we have studied their stability of the fixed point periodic response, and next module will study about different vibration response, that is free vibration response, force vibration response and response of parametrically excited system. Thank you.